Hello. So welcome back. This is another class on, we started with deep neural networks. So we are going to continue, and I've exactly maintained it at the slide that I left last class, which was, if you recollect, I was talking about an automated way, given some three measurements of glucose level, body mass index, and insulin, whether we can automate and find out whether the person or the patient has diabetes. Okay, and so if you have some historical data, right, where I have actually measured the BMI, the insulin, and glucose, and asked doctors to diagnose whether the person is diabetic or not. So I have a lot of this data collected. So here the decision is whether that person is diabetic or not based on these observations, right? And therefore, if it's not diabetic, we are going to label them as 0 class, and if they are diabetic, we are going to label them as 1. Okay. Now we want to develop an automatic way, because doctors may not be available. I mean, we may have a large population. We might need to know, address people in the rural areas where access to doctors might be very difficult. So can we build some systems? Okay, and as I pointed out last class, many of these things are taken from Professor Corney's slides. So next one class or something, after once I start going into speech and all that, it will come back to a lot of my own material. But here I should thank Professor Corney for things being available, right, for us. Okay, so this basic building an automatic system in neural network sort of terminal jargon means that I basically am training the neural network. So what is training the neural network? What does it mean? If I have a neural network like here, right, where I'm assuming that there are 3 input nodes, that means 3 features are going to be feeding, which is what we are thinking will happen in the diabetes problem. Then there is this nodes that take the linear combination inputs, apply a non-linearity here, right? That is what we call as a hidden layer, okay, which is another aspect of it. And then the outputs of this again are linearly combined. Then we have an output here, and here the output is again going to be non-linear. It's going to make only 2 values of output, 0 or 1, right? And because we ideally want these non-linearities to do something, right? So that's what we are planning to do. Okay. Now to train the neural network, we will see what we want it to either classify as 0 or 1. Okay. So that is the goal that we are planning to do here. Okay. So now, and this could be a sigmoid or something sitting there, right? So the non-linearity here. Okay. So now the training means that what is not known in all of this. I know input, right? I know for this, these are the input, the desired output is 0, right? When these are the inputs, or when I give these 3 inputs, the desired should be 0. When I give these 3 inputs, 6.4, 2.8, 1.7, I know that the output should be 1, or desired output should be 1. What is the only thing that I can control here? I can only control what's the weights and the bias, of course, bias ka weights. Okay, so I can only control the weights, right? And so the weights are what we are going to learn, right? And we are going to learn with a lot of data, such that the weights are going to be adjusted or adapted, so that I keep making better and better decisions, outputs, right? So if I put some random weights here, right, I can put some random values there, right? I'll get some random value at the output, right? But it may not be close to 0. So that means I am making errors, right? So I am going to use some method to adjust the weights such that the error keeps reducing. Okay, and that is the basic idea of what is called training the neural network. Okay, so why is it called a feed forward? Because the input is coming from the left, right? So it's feeding from the left, then it's going to the hidden layer from left to right, right? And then from the hidden layer, it's going to the output, right? So it's going forward direction only, one direction only, from left, then it goes to hidden layer, then the hidden layer outputs are fed to the output layer, right? Input layer, outputs of the input layer go to the hidden layer, outputs of the hidden layer go to the output layer. So the data is moving in only one direction, or everything is moving in one direction. So it is in the feed forward, right? It's feeding only the forward direction. Left to right we think is the forward direction, right? So right to left will be, because when you write we are going this, so it's forward, right? So and usually x-axis we say this is positive, right, time as it progresses, right. So how are you going to train this neural network, right? So the way we are going to do is, first we are going to initialize this random weights, okay. This is where a lot of the ideas, initially there were people who were struggling, okay, with these ideas of how should we pre-train or what should be the good values for the weights, okay, and Hinton had some of these ideas. So we will see this is again like an iterative algorithm, just like you have seen multiple times this iterative ideas. So remember, in the Gaussian mixture model, I initialized randomly those weights, and I mean whatever this, the means, variances and the weights, right, and then it did some iterative. Similarly, in the hidden Markov model also, I uniformly segmented, then did some values, found out the GMMs and the states, then I used the states to again realign, right, again I got a different segmentation of the data, then again I updated the parameters, again I resegmented, so that also was iterative. So many of the ideas that we do in real life are all these iterative ideas, what we call as hill climbing ideas. We'll come to that. And so we may not reach the optimal estimates, but at least locally we might be guaranteed some kind of convergence, okay. So initialize with the random weights, that's the first thing we do. So for lack of anything better, you just put some random values there, right. So remember, the weights are the only thing that I can control, right, inputs are these guys. So now if I put this random weights, what will I do? I take the first input values, right. So they are 1.4, 2.7, 1.9, right. This is called forward pass. Then these weights are already known to us now, no? So we multiply these weights, then pass it through the non-linearity. Again, these weights we know they are all random, some random values are already assigned. Then again will come here and some output will come, right. This output, of course, some non-linearity is there also, okay. So now the output should ideally be 0, right, but it will not be 0 because I have not done anything, right, passed through some random values, right, and therefore there is no reason why I should get some good values, right. So we get a value of 0.8, right. So actually desired value should be 0, but we get 0.8, right. So there is an error, right. So what is the error? This is called the predicted value and the desired value is 0, so the error is 0.8. Normally we error, whether it's minus or plus, both are harmful, right. So we take some absolute value, but normally we prefer something called concave, so that it's a smooth function and so on. So we take usually square of this, but let's not worry about here. So there is an error of 0.8. So this is the error, okay. So this is called the loss function, right. So this, what is this? This error is there, and we are going to now optimize. So now what can we do to reduce this error? The only thing we can do is change the weights. So we adjust the weights, but how should I adjust the weights? If I had got perfect value, that means my weights are probably good, so I should not be adjusting. So how I adjust the weights, how much I adjust the weights should be a function of the error. So the adjusting of the weights will depend on the error, okay. So that is why we will do something called back propagation, and therefore the weights are going to be, the adjustment of the weights are going to depend on the error, okay. Because if the error is going to 0, that means probably I got the correct answer, and if I consistently get the correct answer, it should not be a fluke, only this time I got. If I consistently am doing it, that means my network has trained very well, and therefore it is giving me the correct answer all the time, okay. So we adjust the weights, okay. I am showing it for one value, but usually we take bunch of values called a batch and so on, okay. So then the next, so if I do it for a bunch of values and I've done it, now my new values come. So already from the random weights, we have come to some adjustment of weights to reduce the output error, right. So now I come to 6.4, 2.8, 1.7, right. Again I feed, now it's a forward pass, again the updated weights are going to get multiplied, then again some more updated weights are there, and then I get some value. Now it is coming, probably it has learnt well, that's what he's saying, the neural network is training very well, that's how we'll say, okay. It's coming to 0.9, which is close to 1, that means the error has substantially reduced, right. So the neural network is learning something useful, right. And then again there is an error, right, but then what are we going to do? Again, based on the amount of error, we are going to adjust the weights. If the error is small, the weights are going to small adjustments. If the errors are large, we need to make bigger adjustments in the weights. and we keep repeating. So again I'll go and adjust to reduce this error even further, right. So this is what this hammer, right, I'm going to adjust the values in these different weights, right, to make it more suitable so that the error gets even more reduced. Okay, that is all that we are going to do, and each time we keep repeating this, iterating many millions of times, right, and that's how we reduce the error. Okay, and at a certain point we will see that the error does not reduce any further, it almost saturates, or the weights are not changing at all, right. If the error is almost 0, the weights will stop changing, right. So then once the weights have stopped changing, right, then you say, okay, I stop this. Normally there are many criteria that you can use, or you can say that I'll run it for, I cannot afford to keep on doing it. After some 1,000 times I will stop and say that's my stopping criteria, right. So the beauty of this is that, remember, why are we worried about neural networks? Why as opposed to the conventional classical methods like GMM and so on? Because in GMMs and other methods, we are always going to be looking at decision boundaries that are hyperplanes, that are basically some kind of a linear separation between classes. But if I have classes like this, the gray class and the yellow class, or is it brown? Okay, gray versus brown, right? You can see that the decision boundary is not easy, right? There is no line that can separate the two classes, right? But if you have done the neural network training properly, right, and has not got stuck at some local minima that's really bad, you will find that the neural networks do progress, and you can have very good separation. Means the decision boundary can be complicated, and you see it slowly trying to get the two classes separated, and then it will come to a decision boundary like this, okay, which is beautiful, right. So what it says is, this is the decision boundary for this problem, where the grays are going to be different from the browns. Okay, obviously this is all training data, right. So in the training data, these are the kinds of things I'm noticing, and the weights have got adjusted such that at least the training data, it is able to do a very good separation between the two classes. When the test data comes, depends where the test data actually ends up lying, right. More often than not, it's going to follow the pattern of the training data, and so more often than not, you will also be doing a very correct decision if your training data and the test data match. Okay, so this is the power of neural networks. That's why people are looking at it with great interest. Okay, so the basic idea is that we keep iterating, and we will see that there are local and global minimas, and often how do you drive it towards. So these are all some ideas, there are theories associated with it. So we are not going to go into all of this, but you just get a big picture. Okay, now there are two types. So we need some way of optimizing it, right. So we need some measure, am I improving or not, right. So two common ways that we do are two common types of losses that we deal with are called the mean squared loss, right, where I have the predicted value, right, and the actual desired value. I take the difference and then square it. Okay, the reason is, of course, the derivatives are easier and so on and so on. Where instead of absolute, we could take the absolute value. Okay, but more often than not, we take the mean squared error, right, and this is useful when you're trying to map functions using neural networks and so on. And the other is more from a pattern classification kind of perspective. We use what's called a cross entropy kind of loss, okay, which is basically the desired log y hat, right, and of course what are these k classes are and so on. Okay, so these are the two broad loss functions that we are going to deal with. And remember, when I'm talking about these y hat, the predicted value that comes out, right, it is a function of the values of weights that were there, right. It got multiplied by the weights and the inputs, and then you came to this value, right. Therefore now you are going that this predicted value is dependent on those weights. So therefore I am going to, when I have the dependence, there is a function, then I can talk about how can I adjust the weights which indirectly means that the predicted value will be changed so that I will get lesser error or this value, right. So, if you look at this guy or this guy, right, there is a dependence in this on the weights, right. There is a desired value, but the predicted value is coming. So, there is a dependence on the weights. There are nonlinearity, so it is non-linearly dependent on the weights, okay. But we are going to now use the idea that, you know, if I have some function, right, and it depends on certain parameter, right, if I want to reduce or look at the minima of the function, what do I do? How do I find out the minima or maxima? We have done that several times, even in the Gaussian mixture, even in this. How do I find the minima of a function maxima? You know, where the slope goes to 0, right. So, you know, basically that is the saddle point, and therefore, we are trying to find out what is happening, right, or it is a minima or a maxima, right. So, basically it is turning from negative to 0 to positive, or positive to negative 0, like that, right. So, I want to know where the slope is going to 0. So, that is why I am taking the derivative, right. So, derivatives are going to play a very, very important role, okay. Another type of non-linearity that is important, and this is very, very important, especially in the classification problem, is this idea of softmax, okay. This is also a non-linearity, okay, and this guy is useful when you are trying to give a kind of a probabilistic flavor to the whole problem, okay. So, remember that we have these inputs and all. So, I mean, it could be, this could be many layers, right, the output of the last layer, right. This is where I am going to be talking about. Let us say I am doing a K class problem, right. So, previously in diapties and all, I talked about 0 or 1, a binary class, diaptic or not diaptic, okay. So, it was a 0 or 1 binary problem, male or female, parent or child, right, adult or child, right, black or white, some cat or dog, right. So, you are always doing a binary classification problem, okay. But there are many other problems where you can have emery classification, right. So, for example, if I have one box where people write a number, right, from 0 to 9, right. So, I have a picture of that box, right, and my task is to predict whether that whatever number that I drew, handwriting recognition basically, right, is it 0 or 1 or 2 or 9, right, all the way. So, 0 to 9, so there are 10 classes, right. So, based on the picture, I have a 10 class problem now, okay. And this was one of the first, not neural networks, but the idea of handwriting itself was very important for postal systems in the US, okay. That is how handwriting recognition took off in the 70s, and one of the most important you know, person who worked on it is Professor Srihari in sunny Buffalo, right. So, there are many Indians, remember I told you about Bishnu Atal, right. He actually changed the way we do mobile voice communication, right. Today I am talking to you, you can talk to your parents or mobile phone, your friends, everything, and it sounds as if it is their voice because of the amazing work of Bishnu, right. Similarly, Sri Hari has done a lot of wonderful work in handwriting recognition. It changed the way the postal delivery system worked in the US, okay. So, this is basically a, let us say, a K class, capital K class problem. It could be 0 to 9 that I am somehow recognizing, okay. So, now we use this concept of softmax, and that becomes very important in many, I will often talk about the softmax. So, it is good to now, you know, so we talked about many nonlinearities. We have talked about sigmoid, then we talked about hyperbolic tangent, then we talked about ReLU, right, and now we are going to talk about one more of this guy, okay. We will talk about this guy, softmax, and the idea here is that Z1, Z2 are your linear combination. Remember, in any neuron, two things happen. A linear combination of these inputs happen, which is, you know, there is no nonlinearity, right. It is just a weighted combination of these inputs. So, this is still a linear operation, right. It is a linear combination of all of this input. So, you will get one number here. It is a linear combination of this to this node. You know, the weights are going to be different. So, obviously, Z2 will be a different number, and similarly the weights are different when they come from this for this guy, and similarly capital K. So, you will get K numbers that are coming here, okay. Now, I am going to apply a non-linearity. What is that non-linearity? I take this number and raise e raised to power of that number, okay. Now, this e raised to the power of any number, if you look at e raised to the power of x, right, when x when x is 0, what is it? 1, right? When e to the power of x is 2, e squared. When x is 3, e cubed, and keeps on growing. So it goes exponentially towards a positive direction, right? It's going to blow towards infinity, right? Now if I start going in the negative direction, minus 1, then it is e raised to the power of minus 1, which is 1 by e, right? E raised to the power of 2 is 1, e raised to the power of minus 2 is 1 by e squared. When I go to minus infinity, it is going to go towards 1 by e to the power of infinity, which is 0, right? So now it is going from 0 all the way up to plus infinity, okay? So this guy is only going to go from 0 to plus infinity, so it will never take negative values. So this is non-negative, right? So this e to the power of z1 is non-negative. E to the power of z2 is also non-negative. Whatever be the value of z2, it can be 0, minus 1, plus 1, it will always be non-negative. E to the power of z3. So we take this linear combination, this number I am raising it e to the power of z. So already some non-linearity is coming into the picture, e raised to the power of z of k, right? Now the beauty comes that at this point I am only dependent on this value. E to the power of z2 I am dependent on this value, e to the power of z3 I am dependent on this value, e to the power of zk I am dependent on this value, right? Now in the denominator I am going to take the addition of all of these values, okay? So the non-linearity for this first node, till this point it was linear combination, it's e to the power of z1 depends on this, but in the denominator I am also going to be dependent on e to the power z2, z3. The denominator is the sum of all of these guys, okay? So why am I doing it? We will see that is where the concept of discrimination is going to come, right? Similarly, e to the power of z2 will be z2 raised to the power thing, but again divided by the sum of all of these guys. E to the power of zk is sum of all these guys. So at any softmax for any one particular zi, I can go from 1 to up to capital K, this should be capital K, is e raised to the power of z by all the capital K divided addition of all of this capital K. Now this number is non-zero, right? Now I am adding non-negative. I am adding non-negative numbers here. So all of these are also non-negative, right? And this is also non-negative. So in the denominator, so if I look at this guy, e to the power of z1 will be one of the quantities because I am adding, plus e to the power of z2 and all the other quantities are coming, which are all non-negative. So they are at least they will be 0 or there will be some positive number, right? So when I look at this, this is always non-negative, this is also non-negative, and this is one of the elements in the addition in the denominator. So this number is also available at the denominator, plus some positive quantities are also coming. Therefore, this whole thing will always be between 0 and 1. Correct? It can never be bigger than 1, right? If all the other quantities are also 0, then only this will come to 1, right? So e to the power of z1 should be 1, right? And that is the basic idea of softmax, okay? So it gives you a probabilistic kind of representation, right? So yi is e to the power of I raised to the power of z, right? This should be zi. There is a mistake here. E raised to the power of zi, where one of the i's, right? So z1, z2, z3, I will be, let's say, if I look at y3, it will be or y2, e raised to the power of z2 divided by e raised to the power of z1 plus z2 plus zk. Z2 is available in the denominator, but there are also other quantities that are available, right? And therefore, this will always be between 0 and 1, like probability. It will never go, beyond this. And the summation of all of this is going to give 1, right? So it's exactly behaving like a probability, right? And that's the whole idea of this, right? And why is it discriminative? What do I want to discriminate? If the original class was actually first class, I want the output to be only this one should be 1 and all the others should be 0. That means e raised to the power of z1 should be very high and all the other quantities z2, z3 and all for that particular input, right? Depending on the input, all these values are going to change. These all should go to 0, right? Then only this will go close to 1 because this will be some quantity e power z1. I want in the denominator e power z1 coming, plus all the others should be as small as possible, then only this will go towards 1. So it is discriminated, it is saying make this large and suppress these guys. So it says, since it belongs to first class, only this should be there and make all the other guys go towards 0. Similarly, if this input came from this class, then only the Z3 should be high. So it should force all the others to 0 so that this output becomes 1, right. So that is the whole idea of this discriminated training. It tries to discriminate other guys and push this guy up. So that is the power of this neural network idea that's coming through. The Softmax is helping separate out all those classes, okay. And that's why neural networks are powerful. They always are doing discriminative kind of training, okay. They are trying to say, when you're doing partial classification, push the class that you're interested in and push the other classes away from it so that the separability becomes better and better, okay.